Hello students, have you ever wondered how a camera flash charges up and discharges in an instant? Or how a defibrillator delivers a life-saving jolt? All of that is possible thanks to capacitors, tiny components that can store and release energy very quickly. But where is this energy stored? Well, not in the metallic plates themselves, but in the electric field between them. When we connect a capacitor to a battery, charges are pushed onto the plates. This requires work, and that work is stored as electrostatic potential energy. Now, the amount of energy stored in a capacitor is given by the formula U equals 1 by 2 multiplied by C multiplied by V squared, where U is the energy stored in joules, C is the capacitance in farads, and V is the potential difference across the plates in volts. Capacitors play a vital role in real life, powering flash units, stabilizing voltages, and acting as emergency power supplies in critical circuits. Let's derive this energy formula from scratch. Consider a capacitor being gradually charged. When a small amount of charge, denoted as dq, is added, the voltage across the capacitor at that moment is V equals Q divided by C, where Q is the instantaneous charge and C is the capacitance. The work done in transferring this small charge is dW equals V multiplied by dQ, which becomes dW equals Q divided by C multiplied by dQ. Now, to calculate the total energy, we integrate from zero charge to final charge. Capital question U equals the integral from 0 to capital Q of Q divided by C dQ. This gives us U equals 1 by C multiplied by Q squared divided by 2. So, the energy stored becomes U equals 1 by 2 multiplied by Q squared divided by C. If we use the relation Q equals C multiplied by V, we get to more alternate forms, U equals 1 by 2 multiplied by C multiplied by V squared, and U equals 1 by 2 multiplied by Q multiplied by V. Each of these forms is useful depending on whether charge, voltage, or capacitance is known. Let's go deeper. Where is this energy actually stored? It's in the electric field between the plates, not on the plates themselves. This leads us to the idea of energy density, which is energy stored per unit volume. The formula for energy density is U equals U divided by volume. Now, for a parallel plate capacitor, the energy density can also be expressed in terms of the electric field. It becomes U equals 1 by 2 multiplied by epsilon naught multiplied by E squared, where epsilon naught is the permittivity of free space, approximately equal to 8.85 times 10 to the power minus 12 farad per meter, and E is the electric field, measured in volts per meter. Also, E equals V divided by D, where D is the distance between the plates. So higher electric field means more energy packed per unit volume, which is why insulation and dielectric strength are so important in real circuits. Now, let's explore the impact of dielectric materials. Suppose we insert a dielectric of constant K between the plates. What happens to the energy stored? Let's explore two scenarios. Case 1, the capacitor is disconnected from the battery. That means the charge Q stays constant. The new capacitance becomes K multiplied by C, and since energy is U equals 1 by 2 multiplied by Q squared divided by C, the energy now becomes U equals 1 by 2 multiplied by Q squared divided by K times C, so energy decreases. Case 2, the capacitor remains connected to the battery, so voltage V remains constant. Here, energy becomes U equals 1 by 2 multiplied by K multiplied by C multiplied by V squared, and energy increases. So, dielectrics behave differently based on whether voltage or charge is fixed. This principle is used in designing capacitors for sensors, filters, and even touchscreen devices. Let's bring this to life. Where do we actually use this energy? In camera flashes, capacitors store electrical energy and release it quickly for that bright burst of light. In defibrillators, they store high voltage energy and discharge it to revive a heartbeat. In supercapacitors, used in electric vehicles, energy is absorbed and released during acceleration and braking. In computers, capacitors maintain power momentarily during voltage drops, protecting memory and data. All of this works because capacitors can charge rapidly and discharge even faster, delivering energy just when it's needed most. Let's solve an advanced numerical. A 10 microfarad capacitor is charged to 200 volts and then disconnected from the battery. A dielectric with K equals 5 is inserted. Find the initial and final energy stored. Step 1. Initial energy. Use the formula U equals 1 by 2 multiplied by C multiplied by V squared. Substituting the values, U equals 1 by 2 multiplied by 10 times 10 to the power minus 6 farads multiplied by 200 squared. This gives U equals 0.2 joules. Step 2. After inserting the dielectric, capacitance becomes 50 microfarads. Since the charge remains constant, Q equals C multiplied by V is equal to 10 times 10 to the power minus 6 multiplied by 200 is equal to 2 times 10 to the power minus 3 coulombs. Now, U equals 1 by 2 multiplied by Q squared divided by new capacitance. Substitute the values. U equals 1 by 2 multiplied by 4 times 10 to the power minus 6 divided by 50 times 10 to the power minus 6. This gives U equals 0.04 joules. So the energy drops because we kept the charge fixed while increasing the capacitance with the dielectric. Absolutely. Let's make the final scene more narrative, dramatic, and inspiring so it feels like a cinematic wrap-up, just like a passionate physics teacher ending a powerful classroom session. Alright, let's take a moment and reflect on the journey we've just taken through the invisible world of stored energy. You began by wondering, can something as tiny as a capacitor really hold power? And now, you've seen how capacitors don't just hold charge, they hold possibilities. They store energy in electric fields, silent, invisible, but powerful. And we saw this energy doesn't sit idle, it leaps into action in camera flashes, saves lives in defibrillators, and even helps electric cars recover energy every time they hit the brakes. Remember these three magical forms of the energy formula. U equals 1 by 2 Q squared over C, U equals 1 by 2 CV squared, and U equals 1 by 2 QV. Each one is a window into how nature packages energy in electric fields. We also explored how this energy is not just about numbers, it's about space. Yes, space between the plates, where the field lives, where energy exists, and where science meets design. And we define that energy per unit volume as U equals 1 by 2 epsilon naught E squared, a formula that powers real-world engineering. And when we dropped the dielectric into that space, we saw how that silent layer, invisible, insulating, could either amplify or reduce the energy. Just by shifting the conditions, we transform the behavior of the entire system. So now you know, capacitors are not just passive components. They are energy guardians, timekeepers, and lifesavers. And here's the most exciting part: every time you charge your phone, every time a spacecraft corrects its orbit, every time an electronic circuit fires a pulse, a capacitor, somewhere, is doing its silent job. Physics isn't just in the books, it's in every blink, buzz, and beat of our modern world. So the next time you hear the word capacitor, don't just think of plates and formulas. Think of energy, stored, silent, waiting to spark something extraordinary. Until next time, keep exploring, keep questioning, and remember, In physics, even the smallest gap between plates can hold the biggest ideas. See you in the next adventure.